Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Most people think of manufacturing, they probably imagine cutting metal. A block of aluminum goes into a machine, material is carved away, and eventually you're left with a finished part. It's a process that has been refined for decades and works really well. But what if instead of removing material, you could build a metal part from the ground up? That's called additive manufacturing. And in this episode, we're going to talk about additive manufacturing, and more specifically, metal 3D printing. Using a laser and layers of metal powder, engineers can manufacture parts with shapes that would be impossible to create using traditional methods. Internal cooling channels, lightweight lattices, and highly customized components are all possible because of metal 3D printing. Despite all its promise, though, there's one big problem. As these parts are being printed, many of them need temporary support structures to keep them from collapsing under their own weight or warping because of the intense heat required to print with metal. Those supports do their job during printing, but once their part is finished, they have to be removed. And that's much more difficult than it sounds. Removing these supports is often done with sandpaper or with saws, but that can cause problems in terms of time, cost, and accessibility to the actual supports. So, what if there was a better way that other than these mechanical removal methods? Today's guest, Dr. Owen Hildreth, is a professor of mechanical engineering at Colorado School of Mines. His research focuses on solving this problem. His team has developed new methods for removing metal support structures using electrochemistry. Their goal is making metal 3D printing supports dissolvable. This makes this 3D printing process faster, more efficient, and capable of producing even more complex designs. I'm Drew. Let's dive in. So in 3D printing, parts are often built with temporary support structures that hold everything in place. What exactly are these supports doing, and why are they necessary?
Yeah, so what they're doing kind of varies from printing technique to printing technique. So if you go to what you might see like in high schools and stuff with the polymers extrusion printing, where they take like a, a wire of polymer and they cut it, push it through a heated tip, and it kind of oozes out, and then solidifies as the tip moves back and it has a chance to cool. When that liquid plastic is kind of coming out the tip, it needs something to rest on. So in the polymer community, those supports are there to provide something for the polymer to come down to sit on, so it can cool in place. And then also has a second function: when something cools, solidifies, there's a lot of shrinkage. So shrinkage associated with solidifying, and also shrinkage associated with something that cools. And as something cools, it has a tendency to want to kind of curl in on itself. And if it curls in on itself, you're no longer getting the shape you want. You're getting something that's curled instead of maybe each layer is supposed to be flat. So these supports also help anchor the part down to keep it from deforming. And then normally what happens is you print your part, it has these supports that keep it from deforming, and then people are gonna like kind of cut it off the build platform. If it's metals, they'll cut off the build platform, and then they'll do a heat treatment that removes what are called those residual stresses, the stresses associated with cooling and keeping it from moving when it wants to cool. And then they have to remove those support structures. Does that help explain like why it's there?
Yeah, that's great. And so your research focuses on that thing you mentioned, the removing of these supports after printing. What makes this problem something that's genuinely challenging and something that we need to research rather than being trivial?
Well, a couple of things. It's really expensive to mechanically remove these supports. So when I started this technology, I don't know, 8+ years ago, the go-to strategy for removing these metal supports, because they're metal, so that they're in the polymers, you can snip them off with some scissors or little pliers. And metals, they're really strong, and the stronger the metal, like titanium, the harder they are to snip off. So there's a lot of manual labor involved with that process. The other thing that's really important is the types of things that a printer can print is oftentimes really difficult to manufacture with traditional methods like machining and grinding, forging, etc. So there's this kind of promise with metals 3D printing, I think printing in general is like if you can envision it, you can make it. But say you had like a heat exchanger, kind of like, there's a heat exchanger on your car where it goes through the radiator, there's a heat exchanger. When you have all those internal surfaces, how do you go to remove supports from something that you don't have mechanical access to? So some of the promises of additive manufacturing or 3D printing has been limited by our ability to remove these structures that were necessary for the printing process that you don't actually want in the final, device or object part, whatever it is. Um, so that's why we want to be able to remove them and why they're hard to remove.
Yeah, and so you have a solution to this mechanical limitation. How does your approach work to remove the supports beyond ways that traditional methods can't?
Yeah, so I'll start with like how I got kind of got into this field. Um, Traditional metals 3D printing was something I was actually specifically avoiding when I started my career. Um, just because it's complicated and there's a lot of people working in that field. However, I attended a talk that Timothy Simpson gave when he was at Arizona State University giving a talk on the practical challenges of metals additive manufacturing. And giving that talk because ASU was just recently standing up a metals 3D printing program. So I attended the talk, and during the talk, he kind of showed this picture of some like box or something, some that they had printed at their facility at Sim 3D at Penn State, and they had some undergraduates try to like remove the supports, and it was completely mangled. And whatever this thing was, it no longer looked right because they went at it with Dremels, and the Dremels get dull because that's what they do, and it's just like I don't know. I wish I could describe it. It looked more like a squashed plant than a box. He showed this picture because, like I said, he was talking about the challenges of setting up a metals additive manufacturing program, and nobody ever talks about support removal. And he's trying to educate us about the things that we aren't aware of because nobody talks about them. And when he showed this picture, he jokingly asked the audience, "Does anybody know of a water-soluble metal?" And everybody kind of chuckled. And he said that because in the polymers, you can get these support materials that you put them in water, like they print like normal, and they support your structure through the printing process. Um, and when you've done, you put the whole thing in water, and those polymer supports dissolve away, but your PLA or nylon, whatever you're printing, your regular plastic part you wanted is still there. It doesn't care about water. So everybody kind of chuckled, but I thought, well, um, other than like gold, platinum, and maybe palladium, most metals dissolve if you put them in something like in the ocean, is what I was thinking. So the challenge isn't how do you dissolve a metal? That's easy. We've known how to dissolve metals for hundreds of years. Really, this challenge is like how do you dissolve only the thing you want to dissolve? And at first, the first idea I had with Timothy Simpson is they had this printer that called a directed energy deposition printer that could print multiple different types of materials. So I said, why don't you just print the support structure out of something that has low corrosion resistance? So we came up with this scheme is we made a support out of carbon steel and the part out of stainless steel. And carbon steel is really easy to dissolve. Technically, you could probably dissolve a carbon steel in like tomato juice or an onion. If you ever go through like a cooking phase, people go through this phase where they want like a nice carbon steel knife and they sharpen it and they get it nice and shiny and then they cut their onion. And if you don't wash it right away, the acids from the onion will oxidize that carbon steel. So that's why I taught. So that's the first thing we did was to just print two different materials like they do in polymers. And when I was out there at Penn State when they were printing it, um, Tim was showing me other metals printing techniques. One was called powder bed fusion. And on that one at the time, you could only do one material at a time, realistically. And they have a completely different support structure. So we can't play that trick. of having two different materials. And he said, really got to figure out how to get it working with this other type of printing process where the supports of this honeycomb structure, like little thin walls that go up, but it's all one material. So that's what I kind of pivoted to next, was figuring out how to get it working when you could only print one material. And I talked a lot, so I want to pause and see if you have any questions before I explain how that technique works.
No, I'd love to understand how you can dissolve supports while they're same material as your actual print.
Yeah, so the trick was, and I don't know if I have any samples here, but if you look at these support structures for powered by fusion, oftentimes they're really thin. So kind of picture like a beehive honeycomb without any honey in it. It's just a bunch of very thin walls. So for all intents and purposes, these support structures are nothing but surface, or a high surface, very thin, high surface area. So the challenge is, how do you remove a large volume of material? Because there is a lot of support structures, but only remove a little bit off the surface. And people are trying different chemical techniques where you just put everything in and dissolve it. But the challenge is, once again, you have this large volume of support structures, and they don't always have the same axis. Like if you look at this, I'm sure you hear this outer surface is easy accessible, but inside that outer surface is another layer of supports with another layer of supports. So while you're trying to dissolve away all those interior supports as they slowly get exposed, you're also removing material from your part, which you didn't want to remove from. So what I decided to do, the idea I had was, what if after printing, it's all printed under normal conditions, what if after printing, I change the composition of my surface? And since the supports are all surface, their composition fully changes, but the bulk material only has that change in its surface. So the first thing I did was I was working with stainless steel, and I remembered a friend of mine studied corrosion in what's called duplex stainless steel. I remember him saying something about carbide precipitates degrade performance. It's just a little saying he said it as a side, and it kind of stuck in my brain and popped out. So I said, well, what if after printing, when I have my part, I expose it to carbon at high temperature such that the carbon diffuses in to the material. And what carbon does to stainless steel is it reacts with chromium to form what are called chromium carbide precipitates. And stainless steel is stainless because it has a lot of chromium in it. So I have this unique piece of stainless steel, and you've exposed a new surface, and there's like iron exposed or chromium exposed. What happens is this chromium, there's so much of it that it quickly forms this chromium oxide oxide layer that protects the rest of the material underneath it. Okay, kind of like how an M&M has that shell that protects the chocolate underneath. So hypothetically, you don't get chocolate all over you when you eat M&Ms. Okay, it's the same type of thing. Only imagine that shell forming when you broke open the M&M. It forms a new shell on the inside and protects that remaining chocolate. That's kind of what chromium's doing. And when you diffuse carbon in and you form these chromium carbide precipitates, now you don't have chromium in metallic form to reform those what are called passivating surfaces. We've effectively transformed our surface from stainless steel, which has a lot of chromium in metallic form, to carbon steel, where all that chromium that used to be there is now stuck in these chromium carbides. And carbon steel, we can dissolve very easily compared to stainless steel. So now I have the surface has changed from, like I said, stainless steel to carbon steel. Now I can dissolve it under conditions where that it's called sensitizing. We've made it more sensitive to corrosion. I can dissolve that sensitized surface away. And the net benefit is you can now go from a part that's really complex with supports to something like this with no effort. And we ended up with having smoother surfaces because there's a lot of like surface roughness. The surfaces of a 3D printed metal part aren't perfectly smooth. So you actually end up with smoother surfaces afterwards.
So obviously this is very useful for both making more complex parts and for smoothing out the surface, as you just mentioned. What needs to happen for these dissolvable supports to become a technology that's widely implemented?
Somebody has to commercialize it. So I got talked into starting a company. I was the CTO, and it just didn't go well. It was COVID. My mom was dying. Other people's parents were dying. Not of COVID. It was cancer and other things. There was just too much stress. So I went and found some people to take over the IP, and they were making some progress, and other personal stuff happened in their lives, so they dropped the technology. So all it takes is somebody who's interested. I still have companies emailing me today saying, "When's it available?" But I have learned that I am personally ill-suited to running a company. It takes, like, a different set of skills and be able to handle risk and the emotional ups and downs of that. So if somebody wants the IP, it's available. They can contact Colorado School of Mines, and get the IP and run with it. I have, like, a list of 30 or 40 companies that are just waiting the for a company to be set up so they can send parts to. But that's literally the only thing is there's starting a company is not something I'm good at. I'm good at being a professor and inventing new things in science. I have the wrong skill set for getting funds and hiring people and all that other stuff that a good CEO, CTO needs to do.
Well, awesome. That's all the questions I have for you. Thank you so much.
Okay. Yeah, thanks for reaching out, Andrew.
Yeah.
Yeah, if you're right down the street. So, have you are you interested in 3D printing specifically? I noticed like your podcast covers a zillion things.
I mean, it's all stuff that I'm interested in. Obviously, so what I did to find specific people is in this case I looked on the Minds website because it's nearby, and I looked through professors and looked at research, and I'm like, oh, this looks really cool to me because it's something that's new, and it's really practical, and it's kind of chemistry, intersection of chemistry and physics, and um, that's
Yeah.
what I think I'm most passionate about.
Well,
And so yeah,
if you come up here when your brother starts or something, and there's like a big moving day, feel free to stop by and ping me,
yeah,
and I'll give you a little tour of the facilities of anything I can access to that you're interested in. Um, just let me know.
yeah, I would love to.
And then I don't have any money now. I don't need funding now, but I've got some grants I submitted. And next summer, next year, if those go through, let me know. Maybe I can get you some lab work
That'd be
for,
amazing.
yeah, I've got most of my research is in reactive inks. I print chemical reactions instead of particles. So like I can print glass at ADC and stuff like that. So I've always got little projects that need help. And then I'm trying to get some funding from DARPA on a new way of separating elements, and that just needs some what I call minion work. I'm not trying to be dismissive, but like stuff where we just need bodies doing stuff and collecting
Uh,
data. And it's kind of a good fit for somebody who's young and interested. So that always looks good on a scholarship application, stuff like that. If you're interested, it's going to be fun. Don't do it because the chance of getting a scholarship's low.
yeah, no, it definitely sounds interesting to me, and
Yeah.
I really appreciate that. I'm gonna write that down.
Yeah, I'll pay if the funding comes through. I'll ping you because how far away from my are you in mines?
It's 30 minutes max.
Yeah, that's close enough for like a little. I don't know if you have a summer internship or job or anything.
No, I was
Uh,
hoping I could get something figured out, but I understand it's a little bit late.
well, I just have no money. I've been spending all my time working on this new element separation idea. I haven't written enough grants. Otherwise, usually I'm flush with mad cash, as we used to say when I was younger. Um, but this time I've just been instead of writing grants, I've been working in a lab. But I finally got it working. But if it goes through, I'll ping you because there's
Yeah.
nothing more interesting than working with somebody who's excited about stuff and learning.
Uh-huh. Well, thank you so much.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.